12. Name T. Um, 1, 2, 4, 5, 6.
Is it hexene?
No.
Sir, hexene, hex, hextween.
Try going with an IUPAC name. You're putting all of them in a straight single chain. Think about it. Because
2, 3
molecular formula
The
doesn't
2,3-methyl butene.
butene. 2,3-methyl 2-butene.
No, still mistakes. Try converting it from a skeletal form to a structural form first, then mark the branches, give them the numbers for the straight longest parent chain, and then try going with a name. There's a small mistake that you're still doing. You're correct
Uh,
with the stuff
two,
that it is going to be butene. That's fine, that's right. But think about the branches properly.
2,3-dimethyl butene.
2,3-dimethylbutene. You were missing the small di part in there, right? So I'll be very fast and straightforward. This is first carbon, this is second carbon, this is third carbon, this is fourth carbon. So there is one branch over here, there is one branch over here. If I go with the numbering, that's 2, 3, and that's dimethyl. So 2, 3, dimethyl, and then but 2 E. Now, as I've been saying it all along, and I'll say it again, 2, 3 represents the position of the branches. Di means there are two. Meth means single carbon-based branches. Al means the branches are singly bonded. But means there are 4 carbon atoms in total in the parent chain. 2 means the double bond starts at the lowest possible number of second carbon. Ene means there is a double bond. That's how the whole name caters the structural formula. All right, moving on.
Draw the skeletal formula for structural isomer of T that shows cis or trans geometrical isomerism.
Come on, this should be easy. An isomer that has cis-trans isomerism. You can find out any structural isomer, and since this has 6 carbon atoms, there can be many, but you need to pick one out which can show you cis-trans isomerism. And almost any alkene can do that. आपने तो मुझसे IGCSE नहीं पढ़ी, लेकिन जिसने मुझसे IGCSE पढ़ी है उसे अब डांट पड़नी चाहिए कि नहीं? चलें, good.
Sir, double bond second वाली slow.
Very good. So, Laib, I hope you remember the facts that I told you back in IGCSE. The two most simplest way of drawing an isomer, a structural isomer. I'm not talking about cis trans yet. Just a structural isomer is that you convert the branch chain structure into a straight chain structure, or vice versa. First method, second method, change the position of the functional group. So if you apply the first method, since this has 6 carbon atoms, but it's a branch chain structure, if you convert it into a hexene, whether that's hex2-ene or whether that's hex3-ene, both of them can easily show cis-trans isomerism. There are many other options as well. This question does not have a single answer or 2 answers or 3. In fact, it has more. But yeah, these are the most obvious ones or the easiest ones that we can go with. जी साद, आप कुछ कह रहे थे?
Sir, saying the same thing.
Good. Okay, so I hope this clarifies it. Moving on, C.
Each carbon atom in T forms a sigma bond to at least one other carbon atom as shown on the diagram. Draw the orbitals that represent the pi bond that is also present in T. Pi bond is sp2 and sp hybridization.
Perfect answer. A lip-shaped structure can easily tell the examiner that there exists a pi bond for which the density of electron is above and below the central line. All right, lip-shaped structure. So that's a very good response. What about C2?
State the hybridization of the two carbon atoms between which the pi bond forms. sp2 and sp.
You need to pick one answer. They're talking about these two carbon atoms. You aren't supposed to give two answers. They're talking about these two carbon atoms specifically.
SP.
sp2.
sp2. Remember, double bond is sp2 and triple bond is sp. Since they're forming a double bond, which you just represented, right? So sp2. Okay. If they were forming a triple bond, that would have been sp. So moving on. D.
A reaction scheme starting with T is shown. Reaction 2 occurs in the presence of a catalyst. Knowledge of the mechanism for this reaction is not required. Give the reagents and conditions for reaction 1.
Cold dilute cheminophore.
Hexene 2.
Perfect. Remember, diols in the whole book of organic chemistry, 14 to 18, the total part forms diols in a single reaction, that is cold dilute cheminophore, acidified potassium manganate 7. with alkene. And that's what you have over here. Okay, so as soon as you write KMNO4 or potassium manganese 7, it gives the reagents. As soon as you write cold dilute with it, it gives the condition. So part 2 for the same. So this doesn't exactly belong to chapter 14, but yeah, we can go on with it. Since we recently did chapter 18, this shouldn't be a problem.
State and explain how 2,4-dinitrophenylhydrazine 2,4-D and pH can be used to detect the presence of V as a product of reaction 2.
The reaction 2 is a ketone, so it gives positive result with ketone.
Sorry, I was talking with the mute on. This is a 2 marks question, and just saying that it's a positive result won't make sense without telling what the observation would be, because remember, this is an explanation question. So what would be the observation if the test is positive? That is what the second mark stands for. And Aiba, this
I remember it was a color
clearly
change.
tells us this is a ketone. So ketones give positive test with 2,4-D and pH. And Saad, you were saying?
So I remember it was a color change, but I don't remember the color.
Okay, it wasn't simply a color change, it was a color change due to precipitate formation. And it was
The yellowish.
orange-red. Orange-red precipitate, a yellow-orange precipitate. Writing simply yellow won't cut it. So I usually recommend my students to either include orange or red word with it. Means a double color shade. That's better. Orange alone can also work. Okay. So yeah, orange red precipitate with 2,4-D and pH telling us that there is a ketone in the structure. So you get 2 marks. First for telling the ketone. You may also use the words such as carbonyl group. You may tell the complete homologous series. It is entirely up to you. Both perceptions are correct. Both perceptions will get you the mark. Okay, moving on. We go with the carbonyl group because 2,4-D and pH actually tests carbonyl group as a whole, which includes ketones as well as aldehydes. So whether it was a ketone or it was an aldehyde, both things would work. Both way 2,4-D and pH would work. Okay, moving on. Number 3.
The progress of reaction 2 can be monitored by infrared spectroscopy. The absorption caused by OH bonds is always present because water is used as a solvent. Identify 2 absorptions and the bonds responsible for these absorptions, whose appearance will change significantly during the reaction.
Okay, Labby, you were just telling me about the test of the specific chapters. Which chapters you just stated?
Chapter 14 and 15.
It is not 14 and 15. This actually is the last topic of 18. If you'd like to skip it, we can. It's entirely up to you.
Yes, sir, let's skip it.
Okay, moving on. This one is also the same. If almost every reaction, apart from this reaction 6, almost every reaction is out of chapter 14 and 15.
Sir, let's just skip it because I'm not done with chapter 18.
Yeah, this one is a good one. Okay. No, but since you won't be able to find out X,
Sir, we can see from the skeletal formula that it is in alcohol X.
but yeah, this one's X. The structure is given. Okay. Okay, that's right. We can always take help from this one. Remember this, 3 bars, and then we have OH and CH3 in between. So yeah, we can always take this one and we can draw it over here. So we had 3 bars, and then this one, OH. I guess it was the same. So just to make sure we're not making mistakes, yeah. Go ahead and go for part 4. Annotations are also on if you'd like to do it on a piece of paper or annotate over my screen. It's entirely up to you. The drawing of this specific question, Saad, would also give us a clear idea of what we were doing, uh, uh, I believe, yesterday or the day before yesterday about drawing the optical isomers and making sure about the tetrahedral structures that we need to in case of the mirror image of 2 optical isomers. So make sure you keep in mind the tetrahedral structure.
So is this okay?
Okay, if I'm correct, you are representing H and OH with straight lines, C3H7 with a wedge, and CH3 with dotted lines, right?
Yes, sir.
Okay, let's go with the mirror image to get a better idea. This one has mistakes, but let's start with the mirror image first, and then we'll clear this one out.
None, sir.
Okay, the main mistake you're making is that you are taking C3H7, but it's not C3H7. You can take a look at this. This is the carbon that you are putting over here. Then you have this OH, which is here, and then the CH3 over here. And definitely it's also connected to an H, which you are putting. You notice 1 carbon, 2 carbon, 3 carbon, 4 carbon. Even the number of carbon atoms are wrong. Hydrogen are also wrong. I'm not saying hydrogen is correct, but the basics of 4 carbon atoms over here is not correct. To be right, this is C4H9, but writing it C4H9 will not cut it because it will give the reader or the examiner the idea that this must be something like this. No, my bad. Of course, not the last part. Like this, without an H, which means it's capable of forming one bond, which is not right. So let's break it down into parts. Okay, so this is C, this is CH3, CH3, CH3. So it's better if I don't write this and I write C into CH3 thrice. That's a much better way of writing it. Therefore, it also tells us that it's C4H9, but it's not a straight chain. In fact, one carbon is connected to 3 methyl groups. That tells us about the structure exactly. One thing. Second thing, the one that I started off with, discussing the tetrahedral ones. So this structure should not be drawn this way. Let me correct it. H and OH like this. It has to be tetrahedral, right? And then CH3 like this, and then a wedge over here. Okay, and this can be C and CH3, and of course thrice. Okay, from that I mean you need to go with this kind of structure. And of course, one of them can be the wedge, one of them can be the dotted line, and 2 of them can be the straight lines to give the idea of the optical isomerism. And do the same over here. So if one of them is like this, let's say you draw the dotted part over here. In fact, I shouldn't be doing this. You draw the wedge over here, the dotted line, the straight line over here, and the dotted line over here. Then the mirror image should give us the dotted line over here, the straight over here, and the wedge over here. This is what it should be like. This gives examiner the idea that you are still going with the conventional thing that we did back in IGCSE with up, down, right, left, and up, down, right, left, which is not right, which they sometimes write in the marking scheme, but that's definitely what we do not advise our students to go for.
Also got it.
Okay, so this actually answers the question we were discussing on that day. I didn't have the whole question. I could only see what you did. So I had the idea. I had to assume that whatever structure you were drawing was correct. I only wanted to show you how the mirror images should look like. Hence the tetragonal approach. And I hope
Okay,
this
sir.
clarifies everything to Laiba as well. Or do you have any questions,
Yes.
Laiba?
Yes, sir, it's clear.
Good, good. I hope everything
So
is
the next
clear.
one is the next one concentrated sulfuric acid.
Just a second, I didn't even read it. Both optical isomers can be dehydrated to form a single product. Yes, it is. And you can go with this, you can go with something different. Since we have discussed many options for reagents and conditions for the dehydration of alcohol. So yeah, you can go with that. You can go with alumina, heated alumina. You can go with H3PO4 concentrated. You can go with concentrated sulfuric acid. So there are many options that you can go with. Concentrated sulfuric acid being the easiest one. And what are they talking about? This is not out of this chapter, by the way. This is definitely chapter number 16. No, chapter number 17, if I'm right. Chapter number 17, but there we are going to have a double bond. We can't have a double bond over here. Why? Because this carbon don't even have the hydrogen atom. Okay, so the hydrogen has to be taken out of the adjacent carbon, and this is that carbon. This can't be the carbon. So OH out of this in this elimination reaction, H out of here. That's how we get it. Okay. I hope this answers this part. Okay, let's see what is Y. Now, you already know what Y is, so I hope you can go with Z, addition polymer. I'm going to go for this one. I'm going to erase a little bit of it over here. So it's
So Y is
addition.
an alkene, right?
Yeah, Y is the alkene that I just talked about, single product. So let's clear out what Y is. So this is going to be like this. CH3, CH3. This should be a little bit over here, CH3. Okay, and we have the C double bond CH2, and this is of course CH, and this is OH. Now, this is the molecule Y. Go ahead and draw a repeat unit of C. My bad, I'm making a big mistake. Of course, we'll eliminate this OH. Big mistake, sorry. We eliminated this H and this OH to form the alpha. Now the entire diagonal setting should be easy.
One second, sir. I just found a mistake. So in this area, are there are three CH3s, right?
Right. C into CH3 is 3.
Should it be like this?
No, of course not. You're supposed to draw a repeat unit of a polymer.
Sir, so we will remove one hydrogen from the end.
No, we do not remove anything from the structure remains the same. We never remove anything out of it. That's not how it works. These continuations should only be against the doubly bonded carbon atoms, while your continuation talks about the singly bonded ones. and I have no idea how you are adding hydrogen atoms to it. We can't really add hydrogen atoms. Hydrogens are added in hydrogenation, not in addition polymerization. In addition polymerization, technically just structure stays the same. We just break down the double bond into a single bond, converting unsaturation into saturation, allowing them to continue for a big polymer. Okay. So what you're supposed to do every time is that this kind of structure would be a big mistake. So first you need to convert it into this part. Always convert it into this kind of structure for an addition polymerization. Now look at this. These are the doubly bonded carbon atoms. One of them has two hydrogens, one and one. One of them has one hydrogen and this whole structure on the other end. So one hydrogen and this whole structure, which be C and CH3s, and there are three actually in number. So you take this, and this is pretty easy. C double single bond C, 1, 2, 3, 4. Up top, both bonds. This time they're not diagonal. In C and CH3, and that's 3. So this whole thing like this whole thing like this. There you go. This would be converted into this. So every time, no matter how complicated your structure is, write them as doubly bonded diagonal. This would make the entire polymerization easier for you. Why you would specifically concentrate on the double bond of carbon and all the diagonals on it. Make sense?
Yes.
अब आपके लिए भी easy हो गया?
Yes, sir.
Very good. अगर साथ यहाँ पे annotate करते हैं तो आप भी इस corner में annotate कर सकते हैं. If not, if you're doing it on a piece of paper, you can keep sending me the pictures. That's fine. We can even discuss those over here. Okay, 7 exactly isn't an organic question. Well, if it doesn't proceed quickly at room temperature, it must be because the activation energy is high. Okay, that's not exactly an organic question. Okay. The reason why they picked this question is definitely part C and onwards. Let's start with part C.
Triphenylphosphine is used in a type of reaction known as Whiting's reaction. Give the empirical formula of triphenylphosphine.
Sir, C3H6P or PC3H6.
No, that's not correct. Think again. Remember, it's an empirical formula.
Sir, C6H3P.
Still incorrect.
C6H5P.
Still incorrect. It would be better if you take out the molecular formula first and then convert it into empirical formula by taking the simplest whole number ratio. Go with the very basic idea that we usually go with every single time. What you can do is that you can tell me the molecular formula first, and you can then tell me
Sir,
the empirical formula after.
C18 H15P.
Okay, that's the molecular formula. Good. What about the empirical formula?
Sir, 18 and 15 are divisible by 3.
Okay, so the answer to empirical formula would be
P6 H5.
C18H15P is the final answer.
yes, it's the final answer. You cannot simplify it further. Why? Because there is a single atom in there. Imagine C is 18, H is 15, and then we have P. P is 1. 1 cannot be divided by any other number except 1 itself. So this has to be the molecular formula as well as the empirical formula. So it stays the same. So C18, H15P, you don't even need to write that one. And this gives you a very good idea. If you have a single atom in a molecular formula, you cannot simplify it any further whatsoever. So this is the answer. Enough? Okay. After that trick, wow. None of this belongs to chapter 14 or even 15. Type of reactions cannot be catered just because they're introduced in chapter 14. I'm not in favor of that. Okay, let's take a look at G and H. Okay, no, you're simply supposed to draw them. Let's go with D. Part D is definitely from chapter 15.
Identify the organic products formed when compound G, shown below, is heated with hot concentrated acidified magnate ions.
Now, this is an alkene, and depending upon the group's attached and doubly bonded carbon atoms, it gives you different products under harsher conditions, such as hot concentrated acidified manganate 7 ions.
So will a ketone be formed?
Sorry?
So will a ketone be formed?
But you're supposed to identify the organic product, which means the exact formula.
Yes.
Sad, let me know when you're done, when you think you have completed it. Taiba, I want you to answer this question too properly. Either annotate it over here or send me the picture.
Sir, I don't understand.
Okay, let's start.
So
Finish
it
it
is
up
going to form.
first.
They're done. Is this going to be formed?
No, actually, you were previously right with the ketone, forming carboxylic acids, and all of these carboxylic acids definitely not cut it. Okay, I hope that I was hoping that the previous class with alkenes, like a few days earlier, would have got it, but definitely we need to understand how skeletal systems work. So I'm going to make it easier for you, specifically in terms of skeletal systems. Okay. Now remember the rules. If the doubly bonded carbon atom has both hydrogens, it gave us carbon dioxide. Remember the rules. If the hydrogen, the carbon had one H and one R, it was first converted into an aldehyde. Later, it was converted into a carboxylic acid, RCOOH. Okay, RCHO. And in the case if we had both R groups, then this, sorry, my bad, I have to erase this oxygen over here. That is definitely not oxygen. And then this would be converted into RRC double one O, a ketone. Okay, remember this. Now, I'm going to clarify this one. If you have a skeletal structure, then there must be two lines like this, somewhere in between, somewhere at the corner, anywhere these two lines. And this makes sure it is an alkene. Now, how you cater these with a skeletal diagram like this? Because these are structural diagrams, this is a skeletal diagram. This definitely can erase confusion. So let's get started. These means that the double bond would at be the corner of a structure like this. If this happens in double bond is the start of a structure and there's nothing coming out of this double bond. So first of all, you need to break this double bond, and this side means it's going to produce CO2. First hint. If the double bond is in between the structure like this, then it can be recognized in two ways. Take a look at this point of double bond. This point of double bond is giving out two different branches. It's actually a ketone. How would you do this? Break this double bond and this would be converted into a ketone. How? This, this, this double bond and simply O. Move it up, what Sadhbu was doing, and this is what we take out of it. Right? You can either draw the structure, you can write the structural formula, skeletal, it really is up to you. Okay, on this side of double bond, we only have getting one line out of it. So what happens with this one? Exactly at this point, double bond, O, and at this side, OH. Why? Ultimately, it would be converted into a carboxylic acid. If the product is initial, you can simply write H over here, but this H would be converted into OH. That's what we're going to get. So if I write it correctly, that would be this, 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 and there is an O over here and an OH over here. Wait a second. 1, 2, 3. So 1, 2, 3, 4. My bad. This is a carbon 1, 2, 3. So I really shouldn't be drawing this. So this can be erased properly. And that's how it goes, like this. This is your first answer. This is your second answer. These two are the products. And this also gives you the idea how scenario 1, scenario 2, or scenario 3 works. Okay. I hope you get the point by what I was trying to make with
I have a question.
skeletal. Yeah, go ahead.
So which one from these both is getting converted into this?
Sorry?
So there are
None of these. This is
there
first
is
product. I
product,
just
right?
wrote it. And this is from this part. This part is giving this product, which is written like this over here.
Oh, okay, sir.
Okay. There are two products. When you break the double bond, and remember, this is a reaction under harsher conditions, you break this double bond. So this structure gave us a ketone, and that ketone is right over here. And this part gave us a carboxylic acid, right? After Y, okay? And that carboxylic acid is right over here. So we have two products out of it. So this is the second and the third scenario. And usually second or third scenario is the one which happens when the double bond is in the middle of the structure. You can never make carbon dioxide with the double bond being in the middle of the structure. Remember that. You can only make carbon dioxide in this case when double bond is at the start or at the end of any structure, terminal carbon, which I have been calling it all along. Make sense?
Yes, sir.
Good. अब सारा समझ
Sir,
आ गया ना?
sir, what's the name of J?
Name of J.
Like if we
1,
name
2,
it.
3, 4, 5. So it's definitely pent and it's a 2-ene. So it's 2-methyl pent 2-ene.
Okay, sir.
You get the point? This is 1,
Yes,
this
sir.
is 2, this is 3, this is 4, this is 5. Definitely it's 5 carbon atoms, so it's pent. Smallest number 2, pent 2-ene. Since there is an alkyl group over here, so it's 2-methyl pent 2-ene. The name of J. The name of this product would be propanone. Propanone does not have any numbers because propanone is always 2, all right? And this product exactly is going to be 1, 2, 3. So this is propanoic acid. Okay.
Yes, sir.
So that's what we get out of it. Do you understand the complete thing? The point I wanted to make was how to convert the skeletal structures of alkene with under harsher conditions into different organic products for oxidation. If you have gotten that point, that's the one I was trying to make. The other ones are simply side questions. Any questions
Sir,
about this one?
Could you re-explain the formation of carboxylic acid?
Yeah, sure. I think this is too messy, so I need to clean all of this up. Okay. What I want you to do every time, as soon as you look at a structure, break that double bond apart. Since from this part, you have two lines, this can be a ketone. And from this part, you only have one line coming out of this part. So this would turn into an acid. Now, in order to turn into an acid, simply draw it up to this point, right, where you have the double bond, and then draw O and then OH. On one end, double bond O, on the other end, OH. There you go. You simply have your product. Do the same with this part. Draw the same. As soon as you get to this point, draw a doubly bonded oxygen from this point. Now I'm drawing these dots to give you an idea where exactly I am extending it into a carboxylic acid or into a ketone. And the skeletal remains the same. If you understand the sophistication of skeletals, they are actually much easier to work with. But again, the sophistication takes time in practice. So if I break it down into these two dots, one of this dot is exactly extended with a doubly bonded oxygen atom to make a ketone, of course, the carbonyl group. One of them is extended with a doubly bonded oxygen and along with that OH to make it an acid. And I'm using the rest of the structure parts as they were. This is the rest of the structural part as they were. This is the rest of the structural part as they were. Only these are the changes. Out of the circle, we have the changes. I hope that explains it better. Previously, it was much of a mess because I was trying to explain all three scenarios. Now, in this case, it's neater because I'm only explaining the specific molecule J.
Yes, sir.
Good. साद आपको भी clear हो गया? Saad, can you hear me?
I'm sorry, he's in the washroom.
Okay, fine. Assuming that he gets the idea or he can watch the video, so clearing it all up. Okay, let's go with this question. That's a great question. Question number 3, part A.
Below is a list of species which can react with organic compounds. From the list, identify a species which can react with ethane.
Now, this specifically target chapter number 15, reactions of alkanes. Ethane is an alkane. Now, there are specific types or set of reactions that we specified for alkanes. Look at these, and probably only one of the species can react with an alkane. Hence, identify our species. Okay, from the top of your mind, very good. From the top of your mind, tell me the 2 reactions that alkanes go with. There are only 2 reactions in the book that alkanes go with. Alkanes are fairly unreactive.
Yes, substitution and combustion.
Substitution and combustion, which means either it would be a halogen or it would be oxygen. And out of those 2, we only have a halogen over here. Good. Part 2.
From the list, identify 2 species which can react, which can attack the pi bond in ethene. Which can attack the pi bond in ethene. HCl and H2O.
Okay, good. Now, my question is, why not Cl? Why not CO3 negative 2? Why not CN negative? Your answer is correct, first. Secondly, why are you eradicating the three options that you consider false? If you consider them false, there should be a reason behind it. What's your reason?
Substitution reaction.
What?
Substitution reaction with HCl.
Of course not, beta. They're attacking the pi bond in ethene. That's electrophilic addition. HCl would be added to the double bond, or H2O would be added to the double bond, but not Cn negative or Cl or CO3 negative too. तुक्के तो नहीं लगा रहे. Okay, these are added to the pi bond. Why? Because carbon-carbon double bond is a high electron density portion. Now, these can attack this high electron density portion. Why? Because in HCl, we have a partially positive center that is acting as an electrophile, hence can attack it. In H2O, again, we have a partially positive center. You can work it like this. You can work it like oxygen negative and hydrogen positive. That's completely fine. Again, this can attack this. Now, carbonate is negatively charged. Negatively
Sir,
charged species do not attack the high electron density portions. Same goes for Cn negative. But why can't Cl? We have a halogenation reaction. Yes, Saad, go ahead.
so can't we say that the nitrile attacks the bond in ethene? Ethene.
No, it doesn't. No, it does
Sir, but
not, Peter.
we have a reaction. So we have a reaction.
No, we have a reaction,
Mhm.
but do understand the point that in that reaction, it's electrophilic addition. And Cn negative is a nucleophile. It's not an electrophile. The reaction
Oh,
you're
okay.
talking about is when HCN, and let me clarify, this is the partial positive part, this is the partial negative part. This one is actually attacking this part. Cn negative does not do that. Okay, and it's Cn negative alone. Remember, a negatively charged species should repel the high electron density portions of a double bond. This area, this should repel it, this should repel it. What about this one? We have a chlorination reaction with carbon-carbon double bond, or a bromination reaction, halogenation as a whole that I'm talking about, but you're still eliminating this as an answer. Why? Come on, that's a part of your book. Although that's not a
Sir,
part of
C is a
chapter
minus,
14 or
so
15 exactly. This is a part of
if you,
chapter number 16 in detail, but still, yes, Saad, you were saying?
sir, I was saying that part three you're talking about.
Cl. No, I'm not talking about part 3. I'm talking about Cl. Why is Cl not the right option? The answers over here are HCl and H2O. Sorry, this should be written like this. Why not Cl? We're talking about why carbonate is not the right option over here, why cyanide is not the right
It
option
should
here,
have been
as well as
Cl2.
Cl. It should have been
Sir,
Cl2. Remember, when this comes closer to Cl-Cl bond, one of them becomes this, the other one becomes this, and then this electrophile can attack it. A Cl alone would be electronegative enough not to attack this. This is not possible. Get the point? So it has to be
yes,
Cl2,
sir.
not Cl. Liba, do you get the point?
Yes, sir.
Good. Okay, from the list, identify a species that can be used to distinguish between
Can
solutions of
it
propanoic
be
acid
water?
and propanol.
Sir, water, so it will dissolve the alcohol but not the acid.
It actually dissolves both. Propanoic acid is also soluble in water. However, alcohol is soluble in all proportions. Propanoic acid is a weak acid, but still soluble in water. Won't show much of an acidity, won't give a too low of a pH, but it is soluble because it's a small acid, not a big one, just prop, free carbon in the
So
chain.
chlorine, because it will substitute
It's just Cl.
the alcohol. Yes, it will substitute the alcohol, and in the propanoic acid, I don't think it'll do anything.
And observation, if you're trying to make a point, you are
The
already made a point with.
haloalkane,
Hmm?
haloalkane will be formed.
What would be the relevant observation? How would you observe it's a haloalkane? Yeah, chemically that's a haloalkane.
Color change. Sir,
How?
smell. The smell will be pleasant.
The smell will be pleasant for esters, not for halogenalkanes.
Sir, but I read that the haloalkanes have a pleasant smell.
Hmm? Where is that
So I'm
written?
not sure where I read it, but I
You know,
remember
that's
I
not a
read it.
part of your book. That's definitely not a part of your book. Okay, a chlorine atom alone cannot do the trick. It has to be Cl2. So that's not an option. Water will dissolve both. Again, not an option.
So then HCl,
What would that do?
substitution of the alcohol.
And what would be the observation? This one is really easy. You're just not seeing it.
So a color will be formed.
No colors. Until unless you add an indicator or something like that, you won't be able to talk about the colors. And that you can't do, really. So this is not an option either. So is in this one. Remember this one? Carbonates, when reacting with acids, produce carbon dioxide, which is effervescence, bubbling, which they won't do with propanol. The answer is very simple. Acid plus carbonate ions give you carbon dioxide plus water. Carbon dioxide will give you effervescence. The answer was really easy and actually belonged to a prerequisite back from O levels. इसलिए मैं इतने आराम से चलने दे रहा हूँ because this part has nothing to do with the difficult A level portion. This actually is a prerequisite. I hope you get the point, right?
Yes, sir.
Yes.
Sometimes the easiest of your options is the right answer. कैम्ब्रिज ये करता है कि दो सवाल मुश्किल देके ना तीसरा बहुत बेसिक पूछ लेता है. This is a common technique. This is one of the oldest techniques in the book. आपने दो मुश्किल क्वेश्चन किए होते हैं ना, तीसरे पे आपका दिमाग ऑटोमेटिकली आदि हुआ होता है with thinking about the most complicated of stuff, and you throw away the easiest of things. You don't even think about those. So it's a common Cambridge technique. गौर से सोचना है पेपर के टाइम पे.